Today we're going to learn lesson 3 of unit 4, composite functions. So let's have a look at today's learning goals first. After today's lesson, you will be able to understand and interpret the definition of composite functions. Determine an equation for a composite function given component functions, and evaluate a composite function at a specific value. Okay, so first of all, let's have a look at the definition of composite function. A composite function is a function that depends on another function. It is formed when one function is substituted into another. For example, f of g of x is the composite function that is formed when gx is substituted for x in fx. F of g of x is read as f of g of x. Note that the order of the functions is important. As read from left to right, the second function is substituted into the first function. F of g of x is denoted with this symbol. Okay, so remember f of g of x here is an alternative notation that means the same as f of g of x here. Okay, so these two denotions are the same. All right, so let's use some example questions to illustrate these concepts. First of all, determine the composition of two functions. Suppose we have two functions, fx equals x squared and gx is x plus 3. Determine an equation for each composite function, graph the function, and give its domain and range below. Okay, so we have 1, 2, 3, 4, 5 composite functions. Okay, so I'll give you 15 minutes to think about this question by yourself, and then after that, we'll have a look at the solutions together. Okay. Okay, let's have a look at the solutions. Okay, first question, f of g of x, we can substitute x with gx, right? So fx equals x squared, and then f of g of x is actually gx raised to the power of 2. Gx is x plus 3, so we can substitute gx with x plus 3. And so f of g of x is x squared plus 6x plus 9, right? And also we know that this is a quadratic function, which can be easily sketched in the coordinates as shown on the right, okay? And of course, there are no restrictions on the values of x in this equation. Therefore, the domain is the real number set. This can be verified by inspecting the graph also. Looking at the factored form, f of g of x equals x plus 3 to the power of 2. The graph of this function is a horizontal translation of 3 units to the left of the graph of y equals x squared, okay? And also from the graph, we know that the range is y belongs to the real number set and y is greater than or equal to 0. 0 is the minimum value of y, right? Okay, so this is question A. Next, let's have a look at question B. Again, to determine the composite function y equals g of f of x, we can substitute the function fx for x in the function gx. So g of f of x equals fx plus 3, which is x squared plus 3. And again, this is a quadratic function, and its graph can be generated by vertically translating the graph of y equals x squared up by 3 units, as shown on the right. And of course, the domain of this function is x belongs to the real number set, and the range is y belongs to the real number set, and y is greater than or equal to 3. Okay, note that the different results for part A and B suggest that the order of the component functions of a composite function is important. As you can see here, f of g of x does not equal g of f of x, right? So pay attention to the orders. Okay, so please have a look at this function. It's these two functions first. And let me know if you have any questions. If not, let's continue to question C. Okay, to determine the composite function y equals f of fx, substitute the function fx for x in the function fx. Fx equals x squared, right? So f of x equals fx raised to the power of 2, which is x squared raised to the power of 2, which is x to the power of 4, right? This is a quadratic power function, and its graph is shown on the right. Again, the domain is easily seen to be x belongs to the real number set, and the range is y belongs to the real number set and y is greater than or equal to 0, right? Okay, next one. To determine the composite function y equals g of x, substitute the function gx for x in the function gx. So gx equals x plus 3, right? And then g of x equals gx plus 3, which is x plus 3 plus 3, which is x plus 6. X plus 6 is, of course, a linear function, right? Which can be easily sketched on the coordinates as shown on the right. The domain of this function is, of course, x belongs to the real number set, and range is also the whole real number set, right? Okay, the last question, to determine an expression of y equals the inverse of g of x. It is necessary to determine the inverse function y equals the inverse of gx first, right? So in order to find the inverse function of gx, we need to solve x in terms of y according to the function y equals x plus 3. And the result is y equals x minus 3. Therefore, the inverse function is the inverse of gx is x minus 3, right? And to determine the inverse of g of gx, we can just substitute gx into the inverse of gx. Therefore, the inverse of g of gx is x, right? And also, this is a linear function that crosses the origin. And of course, the domain of this function is a real number set, and the range is also the real number set. Okay. All right, so let's have a look at another example question. Evaluate a composite function. Let ux be x squared plus 3x plus 2, and wx equals the reciprocal of x minus 1. First question is to evaluate u of w of 2. Next, evaluate w of u of minus 3. Okay, I'll give you 10 minutes to think about this question, and after that, we'll have a look at the solutions together. Okay, let's have a look at the solutions together. Question A, actually there are two methods to solve the questions. First, we can first determine u of w of x, right? We can first find the expression of this composite function and then put the x equals 2 in and then solve the u of w of 2, right? So first, in this way, u of w of x is the reciprocal of x minus 1 raised to the power of 2. And then plus 3 times the reciprocal of x minus 1, and then plus 2. And this is the expression of the composite function, right? And if you want to evaluate the function value at x equals 2, we can just put x being 2 into that expression. And the solution is 6. Okay, actually there is another method. In order to solve u of w of x at 2, first we can evaluate w2, right? So we can put x being 2 into the expression of wx, which is 1. Then we can substitute w2 equals 1 into ux, which means u of w of 2 is actually u of 1, right? Which is 1 squared plus 3 times 1 plus 2, which is 6, right? Okay, so this is question A. And for question B, also there are two methods. First, we can determine an expression for w of u of x first, right? So w of u of x is actually the reciprocal of the difference between ux minus 1, which is the reciprocal of x squared plus 3x plus 1. Then in order to evaluate w of u of minus 1, we can just put x being 1 into that expression here. So w of u of minus 1 is 1 over minus 3 squared minus 9 plus 1, which is also 1, right? And there is another method. In order to find w of u of minus 3, we can first evaluate u3, right? u3 is actually minus 3 squared minus 9 plus 2, which is 2, right? Then we can evaluate w of u of minus 3. And actually u minus 3 is 2, right? So w of u of minus 3 is just w of 2, which is 1 over the difference between 2 and 1. And the result is also 1, right? So you can choose either method you like. Actually, for this specific question, method 2 seems a little easier, right? Okay, so let's have a look at another example question. This time, this is a real world problem. So be careful with the domain, right? For a real world problem, when you study the domain, usually you will consider the real situations in this particular problem, okay? Okay, I'll give you 15 minutes to have a look at this question and let's make a summary.